Now, we can also think about tension at the level of the whole muscle. Remember that a muscle like your biceps contains many motor units and many muscle fibers. In order to coordinate the contraction of your biceps, the individual events taking place in all of these individual fibers have to work together. So just for the sake of having some easy math to use in my examples, let's pretend that a muscle contains 50 motor units and 200 muscle fibers. When I'm working that muscle really hard, I want all 200 of those muscle fibers to be generating maximum tension. But when I'm doing a less intensive workout, using all of them is kind of wasteful and unnecessary. But in either situation, I have to have coordination between the motor units and between all those muscle fibers. The other thing I want is for there never to be a situation where every single muscle fiber is relaxed. In other words, even when you don't think you're using a muscle, chances are some of the muscle fibers are in a contracted state. So the percentage of fibers that are contracted at any given point is referred to as the muscle tone. A muscle on your arm most likely doesn't have a lot of tone, especially in my case, but a postural muscle has quite a bit of tone. Now, in order to actually generate more tension and increase the force that's generated, more muscle fibers have to be brought into a state of fused tetanus. So if I was lifting a light object like a textbook, then let's say I'll stimulate 25% of the motor units in my bicep. But if I was lifting a really heavy object, which in my case would be like 2 textbooks, then I would want to use 100% of the motor units. When we lift heavier loads and we need to generate more force, we recruit or bring more motor units to the party. We stimulate more motor units to contract. Remember that motor units don't have to be the same size as well. So when you lift a heavier object and you need to generate more force, you not only want to have more motor units recruited, but you also want to have larger motor units recruited as well. In the image on the left-hand side here, you can see how there's a small amount of tension that's generated when we stimulate the purple motor unit, but there's relatively more tension generated when we stimulate the purple motor unit and the green motor unit. That's recruitment. Now, we also know from before that different motor units can consist of different types of muscle fibers, type 1, type 2A, type 2B. So the graph on the right is showing us that when we're generating the greatest amount of force, we're recruiting type 2B fibers primarily. Remember, those are the ones that give you the short, powerful bursts of muscle tension. The idea of tone and recruitment can be kind of tricky to understand because it's not something that we can see. And that's why, in my opinion, one of the easiest ways to understand the concept is to think about a family of disorders known as dystonias, which are muscle disorders that create a lack of muscle coordination. In other words, a loss of tone. So one example of a dystonia is blepharospasm, which is a muscle spasm in the muscles of the eye that you can see in this video here. Even when his eye muscles are at rest, he's getting that twitch because some of them are being stimulated to contract. And here's a more extreme example, which is Parkinson's disease, a very severe dystonia that actually originates up in the brain.
Hi, I'm AJ. I'm 39 years old and I suffer from Parkinson's disease. I was diagnosed 4 years ago when I was 35, and I've since undergone deep brain stimulation surgery. This is a procedure whereby 2 probes are dropped deep into my brain and hooked up via a wire down my neck to a pacemaker in my chest. This provides a steady stream of electricity to my brain per second. So it has had a major effect on my life and a major effect on my family's life, which is the main thing. And today I'd like to show you what happens when I turn my neurostimulator off. Now, it's just after 11 AM, so it's time that I had my second dose of medication for the morning. So my first dose is pretty much all but worn off. So this is a good example of what I'd be like when I'd be sort of off, with no medication in my system and no power. To show you the dramatic effect, I will demonstrate. This is me with the power on. I'm not making happy little faces for the video. These are tests that the neurologists make us do to test our reflexes. As you can see, they're wiggling, moving fine, and I've got very good movement. This is the remote control, and this checks that I'm on. On and okay. And this is me when I turn it off. Oh, you won't be able to read that, it's shaking too much. So it's almost an instantaneous reaction. I can't control this. Could shake some quality cocktails with the right. The left just looks like the royal wave. My voice is gone. It's harder for me to get words out and speak. I'm completely rigid, and if I tried to stand up I'd fall. If anyone thinks I'm faking this, I'm not. I can't control the tremors and dyskinesia. The twisting in my neck is called dystonia and is really quite uncomfortable. So as you can see, the tremors are getting much worse and I'm in quite a bit of discomfort, and I'm about to drop the remote control, which will be fun because I won't be able to turn my stuff back on. So I think party time is over. Almost automatically the power comes back on and I'm steady. So if anyone's considering DBS, I thoroughly recommend it. It is life-changing. Thanks.
So in this unfortunate case of Parkinson's disease, dystonia really takes two forms. There's muscle contraction when we don't intend to have muscle contraction, and there's inability to contract muscles that we want to contract. Now, one thing that I would point out, and really the reason why I showed you this video, is that even when he's tremoring, if he works really, really hard, he's able to recruit enough motor units to still force himself to do the action that he's intending to do. You know, he's struggling to get that remote back to his chest, but he's able to do it because he's able to recruit the motor units that are under voluntary control still and sort of overpower the ones that are not working properly. So the treatment for dystonias varies based upon the type of dystonia and the severity. Something like deep brain stimulation is obviously very invasive, and so it's a drastic treatment that's often reserved for the most severe cases, like in his case, Parkinson's disease. But in some cases, you can treat dystonia using some of the drugs that we've already talked about previously at the NMJ, or even Botox, which you've probably heard of before. Botox affects the snare proteins on the presynaptic membrane that allow vesicles containing acetylcholine to dock. So in the presence of Botox, acetylcholine can't get released into the synapse. Now, when I was originally putting together the slide set, I tried to find an image showing you the mechanism of action for Botox. And instead, to my horror, I found these images of Botox parties. And the idea there is that muscles contract at the wrong times, pulling on your skin and giving you wrinkles. So people use Botox for cosmetic reasons. But if you go to page 2 of these Botox party images, you'll find pictures of all these people that have been paralyzed because their Botox party host didn't actually have any medical training and injected the drug too deeply or injected it into the wrong spot. Lastly, we're going to be looking at the details of this slide here a little bit more closely when we're together in class, but what it's trying to show are two different types of muscle contractions. Isotonic contractions happen when there's a gradient between the amount of force generated by muscle and the resistance offered by the object being moved. They are characterized by muscle fibers changing size. Isotonic contractions result in a change in muscle fiber size. Isometric contractions, on the other hand, occur when muscles can't generate enough force to actually move an object. So even though the fibers are contracting, they're not able to actually change their length. Instead, the tension that develops is really not from the filament sliding, but from the stretching of elastic proteins in the sarcomere, like, for example, titin, which we'll be looking at in our in-class diagram this week.